Okay, recording started. Welcome to week 8 review session, or not week 8, but review session 8. Today we are talking about frequency domain and impedance and how to solve circuits with that. Basically, AC. Okay. Basically, right, you've learned you know that alternating current exists. The electricity in your walls is alternating current, meaning that the voltage over time, looks like wee with goes up to like 130 something, something like that. Fun fact, when it says that the voltage in the wall is 120, it's the RMS voltage, which you I think know what it is at this point. So anyway, that's what AC is. It's just when the voltage goes up and down. However, when you have alternating current, circuit components behave in ways that can be modeled very nicely by imaginary numbers, and that's where we get impedance. So what we call impedance is impedance is like I will define it as resistance but AC because that's basically what it is. Resistance but AC. So if I have a circuit with an AC signal and it goes through some components, I'll have one of each of the main component types you've learned, right? Resistor, capacitor, and inductor. And let's say this is like 12 volts at a frequency of 5,000 radians per second. Hopefully you all know that like when you have like a function here, the omega t, because you can always assume that these things are in radians unless asked. So this is the frequency in radians per second. If you want to get hertz, which is like times per second, then you know that omega equals 2 pi f. This is like not really relevant to this class, but it might be sometimes. And then f would be omega over 2 pi. Cool. That's a random aside. But anyway, so we're here, right? If we want to figure out what the current in this circuit is, or like the voltage at any point in this circuit is, it would be a huge pain in the ass with what you knew last week, I guess. But now there are things we can do. So we call Z is the impedance. The impedance of a resistor is just the resistance. We'll draw a little resistor. Uh, However, for capacitor and inductor, it's different. So the impedance of a capacitor is equal to 1 over J, where J equals the square root of -1. We call it J in electrical engineering because I is already used up by current, and we don't want to get confused with our variables. So it's J, the frequency, and C, which is the same as -J over omega C. And then for inductors, it is ZL equals J omega L. These are the only things you need to know, really. Like it's just this and this, because this one's easy to remember. But if you know these two things, then there's really like nothing new at all in this unit if you know like how to do math on imaginary numbers, which isn't really covered, but I'll say like a bit about it. But anyway, what this lets you do then is you can transform this circuit into its phasor form or its frequency domain form. So you would plug in the numbers to those things. So here, what this stays as R. This would be 1 over, or I'll say the negative J form is kind of more useful. Negative J over 5,000 times C. And this would be J 5,000 times C, or times L, sorry. And then the one thing I also didn't mention is that if I have some voltage A cosine omega t plus phi, so this is just the most general form you can write this in, where like you all know math, right? If this is like a normal cosine function, That's a sine function, actually. If this is a normal cosine function, then the omega is like how shrinked it is or how wide it is. And then the phi here would be the phase shift. So if I give it a positive phase shift, it'll look like it's shifting the function like to the left, kind of, right? I kind of just drew a sine wave or negative cosine. But that's not really part of this course. Hopefully you all know that already. Um, just to be annoying in this class, or not just to be annoying, it actually makes a lot of sense if you like do engineering. But this will be in radians, and this will be in yeah, the unit for that omega is radians per second, and this is in like degrees. And it makes sense because it's much easier to think about degrees than it is to think about radians. So for the phase shift, you talk about it in degrees, but for this, like frequency, it's just yeah, that's how it works. But anyway, back to the topic at hand. If I have some like voltage or current function, and it is in the time domain written like this, right? Then in the frequency domain, we write it as V bar, and it is a e to the j um phi. So the omega goes away because basically for anything in this class, all of the things in the circuit are going to be running at the same frequency. So here this would become 12 e to the j 0, which is just equal to 12 because we had no phase shift up here. But this, if you don't understand this, I would highly recommend looking up a YouTube video on Euler's identity. Basically, the idea is that if I have I'll go back to like math, e to the I theta, right? This is equal to uh, cosine theta plus I sine theta. So like in the complex plane, if this is real and this is imaginary, like it, you all know the unit circle from trigonometry, right? If I have the unit circle here, basically some point on the unit circle here can be represented as, so this point here is, you know, cosine theta plus j sine theta. Or I'll go back to j because that's what I'm used to. J sine theta, but we can write that nice and succinctly as e to the j theta. So that's what we're doing here. So if you can visualize this in your head, it often makes stuff a lot easier. And then okay, the little bit of complex math you need to know. If I am in this form and I want to go to if I'm in a plus uh JB form or whatever you want to call it, you know, and I want to go to this form, then A, there's like a couple ways you can do it. The way I do it is A equals the square root of A squared plus B squared, right? Because distance formula, we got a right triangle here, Pythagorean theorem, bam. Uh, and then theta equals the inverse tangent of B over A. Again, think about the unit circle. The real part is like the cosine. The imaginary part is the sine. So then this angle is going to be sine over cosine. And it works itself out like that. I think Zorman teaches it like you do this first, and then A equals like um what would it be if I have a theta here and I know A and B, then this line would be let's see, cosine of theta is adjacent over hypotenuse. So then C equals A over cosine theta. I think that's what he teaches. Correct me if I'm wrong. But yeah, you can use either of these. Both of them will work. I think this should work too. I just prefer this one because it's easier for me to remember, and I don't have to reprove it every time I want to use it. Um, that's all the complex math you need to know. Uh, One thing that's good to know, your calculator can do so much of this for you. I might make a video on that, or I made one last year that was kind of okay. I might re-upload it. Uh, but your calculator can do, if you have a TI-84, which I guess is an assumption that probably a lot of you don't have one, but if you do have a TI-84, and probably if you have many other calculators, your calculator can like convert between A plus BI form and the other form for you. You have to just like look at how to do it. It can also like convert between like degrees and radians and all that stuff. So I would highly recommend doing that. However, for this class, you have to show your work even if you do it in a calculator. So like for this class, always show math when converting between A plus JB to A e to the J theta. Okay, cool. With all that out of the way, hopefully this is all review. If it's not, like study up on your math because there it's just going to be assumed that you know it. Um, for the question in chat, do we have to do it in radian mode or do we have to do it in degree mode? Uh, you will always be expected to give your answers in terms of degrees. However, your calculator might not like work nicely for degrees, so you might want to do it in radians for the purposes of calculations, but always give your final answer in terms of degrees for the phase. Always. If you give it in radians, like you'll probably get some points off or something. Yeah. And I'm just gonna start doing practice problems. If I miss some stuff about the math along the way, then it'll come up here. But like, yeah. So let's start with it was this. Yeah, okay. So oh yeah, but then one thing I didn't say. So once you get stuff in terms of impedance, you can treat impedances just like resistances. Like they're the exact same thing. If you know how to simplify a resistor circuit, then you know how to do everything in the frequency domain. So don't overthink things. It's like just resistors. And this will become very clear in this question I'm about to do. So we have Vs of t, capacitor, some of this, some of that. 0.2 millifarads, 0.2 millifarads, 50 ohms, 0.2 henries, and 108.33 microfarads. And we have I of t, and we have Vs of t, and Vs of t just so happens to equal 30.77 sine 200t plus 120 degrees volts. So before we do anything, it's a good practice to convert your sine into cosine. So we will start by doing that. If you forgot, sine of something plus phi or plus theta equals cosine of that same thing plus theta minus 90 degrees. They are 90 degrees offset, and that is the relation. So here we can also write this as, 30.77 cosine 200t plus 30 because 120 minus 90 is 30. But basically we just write everything in terms of cosine for purposes of this class. So that like 0 degrees phase means you have a cosine like centered at 0. And 90 degrees phase would mean, or negative 90 degrees phase would mean you have like a sine. So I don't know, look at Desmos or something. If you're confused about that, just like go to a graphing calculator and mess with it until it makes sense. And this, in terms of phasor, right, to the frequency domain, phasor is the term for like this. This is called a phasor. If I say that word, it just means like the frequency representation of a sine wave, or the imaginary representation of a sine wave. So here, right, this would become V bar equals 30.77 e to the j 30 degrees. Cool. And that's that. And then we have to find the equivalent impedances for all of these components. So for that first capacitor, I'll say ZC1 equals negative j over omega. I'll write them up here. So ZC equals 1 over j omega c equals negative j over omega c. and ZL equals J omega L. And I can put ZR equals R, but hopefully that one's straightforward enough. Um, so we have negative J over omega in this case, right? As you can see from here is 200. So now we have negative J over 200 times 108.33 times 10 to the negative 6, which just so happens to be about negative J 46.16 ohms. Usually we write impedances in like the A plus BI form or A plus BJ form. That inductor I'll do the other capacitor first. So Z2 equals ZC3. Both of those are the 0.2 millifarads. So it's negative J over 200 times 0.2 times 10 to the negative 3 because it's milli. And that gets you negative J 25 ohms. They are in units of ohms, by the way, if I didn't say that earlier. For the inductor, same thing. We use the formula that we're given here. If you're curious about these formulas, I think he explained them in class, but it has to do with like when you take if you take a signals and systems class, they'll cover this, but it has to do with when you take the Fourier transform of the like differential equation. This pops out, and it makes sense if you think about it. Yeah. So J times 200 times 0.2 again, and it's just 0.2 henries, so it's just straight up that. And this is positive J 40 ohms. And then ZR is 50 because it's just 50. So then if we redraw this circuit real quick, right, we can leave the components drawn as they are, but it doesn't, you could just like put them all as boxes. Sometimes they do that just to show that we're like doing this in the frequency domain. But now we got 30.77 e to the J30. Just like that's that. We got negative J 46.16. We got 50. We got negative J 25. We got negative J 25, and we got J 40. So now from here, it's asking you to find this current, right? Which for now we'll call I bar. Oh well, all right. Find I of t. Okay, cool. We're trying to find I bar, and basically that just means we have to simplify all of this into one equivalent impedance or one equivalent resistor, depending on how you want to talk about it. And so how do we do that? We'll just pretend everything is a resistor. I look at this, I see, wow, these three components are in series. So I'll simplify it a bit, and we get that, 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 that's an inductor, trust me. And then this is where we put a box because it doesn't really make sense to think about it anymore as like a component. And I'll call this like Z1. And here we'd have Z1 equals these three components added together. So it's literally just 50 plus negative J25 plus negative J25. Just the same way you do resistors. So this becomes 50 minus 50J, right? And then we look at this and we say, oh, wow, these two are in parallel. This was J40 and this is Z1. So then we'd have these two things in parallel. And how do we do things in parallel? Well, this is where I tell you you should use your calculator because it can do it for you. But if you don't have your calculator, then you can still do it. And let me remind myself how you do this without a calculator real quick because it's kind of a pain in the ass. I mean, it's still like the same thing. So if we want to find Z1 in parallel with the ZL, right? It's going to be, Z1 ZL over Z1 plus ZL, the same way you do like resistors in parallel, which here would be J40 times 50 minus 50J over J40 plus 50 minus 50J. And that equals like 2000 plus J 2000 over 50 minus 10J. And then you can simplify this a whole bunch. You have to like multiply by the conjugate of the denominator. I'm not going to go over this because this is like just a pain in the ass. And if you don't know how to do it, find a YouTube video telling you how to do it. Um, but anyway, dot dot dot, you get 800 over, so like you do some steps, you can like divide everything by 10, multiply by the conjugate 800j over that over 26, and then you get eventually you get 30.77 plus 46.15. What I would do if I were doing this is I would say, okay, I have that initial expression here, right? And then I would go to my calculator and just write that. So if I go to my calculator and I type like I times 40 and then parentheses 50 minus 50 times I and then divided by uh j or I 40 plus 50 minus 50 I, and then I press enter and then I'm in the right like mode for it. Uh I'm in the right mode for it. And then it just like spits out the answer for me. Cool. Learn how to use your calculator. It makes your life a whole lot easier. I don't think you have to show your work for this, but there's other stuff you do have to show your work for. But anyway, we get this. And then there's like one more step. So we're here, and then we have this. So this would be our like Z2, I'll call it. And then this becomes plus minus. We have the capacitor and that Z2. And then the capacitor was negative 46.16 J. So then our final, if we add those two because they're in series, right? We get our like Z equivalent. I'm out of space here. I might go to the next page in a sec. Here, this would just be Z2, Z equivalent equals Z2 plus negative 46.16 J. So if I do that, so that answer minus 46.16 J on my calculator, then we end up with basically just if you get like a very, very small rounding error in this class, or if you get like a very, very small number in this class, you can probably assume it was zero. What mode am I talking about in the calculator? If you have a TI-84 and you press the mode button and you look through it, right? There's the section that says real A plus BI and real to the theta I. And if you pick A plus BI or real to the theta I, then you can use imaginary numbers. And to type in I, you do second period. I'll upload the video I made last year on this after this. Yeah. Anyway, we're here, and this becomes about 30.77. Wow, what a convenient number. It's almost like the question was written in mind. So let's keep going though. We're at plus minus. This was like 30.77 e to the j30. E to the j30. And then this was z equivalent, and this is just 30.77. And we want to find, okay, what is I bar? So just like how it was in real circuits, we still have V bar, or just like we had like V equals IR, right? Now we have V bar equals I bar Z. So here it's just I equals V bar over Z equivalent, which is going to be 30.77 e to the j30 over 30.77. Wow, this question was nice and easy. And you get e to the j30 degrees. And this is not your final answer, remember, because it asked for I of t. So we have to convert back. So by the logic we had here, it's just the same thing in reverse. So here we have essentially a 1 in front. So I of t would be equal to simply cosine of, and the omega stays the same. So it's back to that 200 here. So 200t plus 30 degrees. And this would be, oh, and amps, important. And this would be your final answer for that. Yeah. And I will just keep going. Uh, Okay. This is good. Okay. This is a question kind of just exemplifying that everything you're doing is exactly the same as what you did for real circuits. Because this one, yeah. So this is a frequency domain circuit, but you're going to do node voltage on it. And oftentimes with these circuits, they will come already converted to frequency domain for you. And that just like makes your life a bit easier. Okay, let me see. Okay, yeah. And then we get minus J10, J minus J4, 9, J6, 20 volts, 10 amps, and 30 volts. Okay. And it's asking us, this is VC bar, and it says, write uh, all equations necessary to find VC bar using node voltage. So using node voltage, we're just doing node voltage. You know how to do node voltage. So if we define our ground, which as I've said in previous things is like always just the bottom thing. So we call this 0 volts. Then we look at where our nodes. So nodes again are where more than two different parts meet. So we have here, I'll call this V1. And you might be thinking here, but no, this is the same node. So just don't get tripped up by that, right? So we have V1, right? This is connected, this is all one node. And then the other one we'd have is just this V2. And this isn't a node because it's only connected to 2 points. And also it's just like V1 plus 20, right? Hopefully that's pretty clear. And yeah, that's it. So then we write our equations. So V1 bar. So for node 1, it's just the same way we've done node voltage before. So we got V1 minus negative J10. Oh, wait, no, sorry. I messed that up instantly. V1 minus 0 volts over negative J10, right? Plus V1. Oh, okay, so I did this path, and then I'll do this path, this path, and this path. Or like this path, yeah. But okay, so we have V1 minus V2 over 9. If you want to, you can put the bars here, but you don't really need to. And then for this path, right, we have, okay, what's the current through this path? It's going to be the current across this thing, which is determined by these two, right? So it's going to be V1 plus 20 minus V2 over J6. Same thing we did in the previous lessons. Yeah. And then the last path, okay, we have 10 amps going out. Remember that going out means positive, so 10 amps. And that equals 0. And that would be our first equation, right? Cool. So then for V2, we do much of the same thing. Almost exactly the same thing, in fact. So we got, I'll start with the left path is V2 minus, and then we have that V1 plus 20, and that over J6. And then going down, we have V2 minus V1 over 9. And then going to the right, we have V2 minus 30 over negative J4. And that equals 0. And then finally, because the question asked us everything necessary to find this VC here, it's just going to be, we write a VC equation, and VC pretty clearly is just the voltage difference between V2 and 30. So it's just going to be V2 minus 30 volts. And then these three would just be your answer if you were given a question like this. And that would be it. Take a sip of water. Okay. Um, what else? Okay, this is really straightforward. Yeah. Um, yeah, I'll do this. Okay, so we got this one's like pretty straightforward. We got Just a bunch of components in series. Sorry if my inductors sometimes look like resistors. This is an inductor. You can tell from the unit. And then this is 7 sine 100 t plus 20, which, if you remember, we want to convert this to sine or to cosine. So this is going to be 7 cosine 100 t minus 70 because you subtract 90. Yeah, cool. So if we convert this to the frequency domain, right, I will just draw it in first. Well, we know instantly the resistors are still the same. This is now going to be, remember, we just take the magnitude and then e to the j phase. So it's e to the j negative 70, which I'll write as e to the negative j 70 degrees. And then ZL1 is going to be j times omega. So omega here is 100, right? J times 100 times that 100 times 10 to the negative 3, which turns out to be J10. Does that make sense? Does it? Hmm. Oh, yeah, yeah, duh. Okay. Shouldn't it be 100? Am I stupid? 100 times 100 times 10 to the negative 3. Oh, okay, yeah. I guess I cannot do math in my head, whatever. Okay, ZL2 is J times 100 times 40 times 10 to the negative 3, which gets us J4. And then for the capacitor, we have negative j over 100 times 1 times 10 to the negative 3, which gets us negative j10. And the resistors are just the resistors. I'm not even going to write those down. So now we have j10, we have j4, and we have negative j10. And it's asking us to find, oh, and the question was like, find current through 2 ohm resistor. And if you think about it, every component has the same current flowing through it. So if we have current flowing through the 2 ohm resistor, it's just one current for the whole thing because they're all in series. Um, and yeah, so that just means, okay, we have to find that overall current. So we just have to combine all of these into one. And luckily for us, that's really easy for things in series, right? It's just going to be, you add all of them together. So it's going to be J10 plus 6 plus J4 minus J10 plus 2. These cancel, let's see, and then you're left with 8 plus J4, right? Yeah. So then the current would become 7e to the negative J70 degrees divided by 8 plus J4. And you might be thinking, how do I do this? Hopefully you're not thinking that because you had to do this on the homework. But basically what you do is you either plug this directly into your calculator and it can like low-key do it for you, or what you're supposed to do for this class and what you're supposed to show your work doing is you want to convert this to its a plus ae to the j theta form. So as I said earlier, a is going to be 8 squared plus 4 squared. Let's see what that is. That's the square root of 8 squared plus 4 squared is 8.9.94. And then the theta is going to be the inverse tangent of the imaginary part over the real part. And that's going to be second tan of 4 over 8. And that's going to be 20. Oh, wait. Yeah, I'm doing this right. And that's going to be 26.56 degrees or 57, whatever. But okay, we have that. then we can rewrite this as 7e to the negative j 70 degrees over 8.94 e to the j 26.56 degrees. And so now, if you remember some of your exponent rules from math class, this is where it comes in handy because we can separate this because it's all multiplication into 7 over 8.94 times e to the negative j 70 over e to the j 26.56, which is, whatever that fraction turns out to be, times, and this is the exponent rule. It's j, and then it's the first one, so minus 70, subtracted from the second one, 26.56 degrees. And so if we do that out, we end up getting, okay, this becomes 0.78, and this becomes e to the j, and I'll write in parentheses here just for being explicit, negative 96.56 degrees. And so this is your final I bar. However, remember, basically, if the question starts in time domain, you have to end it in time domain as well. So if we're ending it in time domain, we just have to convert this back to time domain. And we know how to do that. You just like do the inverse of what we did at the beginning with this, right? So the magnitude is just, so I of t is going to be 0.78 cosine of the frequency stays the same, so 100t, and then the phase is minus 96.56 degrees. And that, oh, and amps, important. Don't forget the unit. That would be your final answer. Yeah. I saw a question, for the previous question, how did I get the V1 plus 20? So when we're doing like this term, right? So this is all V1, right? So rewrite that here. So then if I want to find the current going this way, the current going that way, so basically voltage sources, you can think of them like they don't directly affect the current. What's going to affect the current is this. You can think of it as a resistor. What determines the current is the voltage on either side of this impedance box, and either side of this resistor. This is a voltage source, so that means there is a voltage difference of 20 volts between these 2 points. If there's 20-volt difference between this point, and this point is V1, right? We have V1, and then we go up 20 volts. Then up here, we have V1 plus 20. And then if we want to find the current going through here, we have V1 plus 20 here, and we have V2 here, and we have something there, then it's just V1 plus 20 minus V2 over that J6. Hopefully that's clear. Okay, so look at that one a bit more if you want. I still have time, so I will do some more questions, I suppose. Let's see. I did that. Okay, yeah, this works. So this one again has already been converted for you. And it says find the voltage across the inductor. So yeah, find the voltage across the inductor. Since everything is in parallel, that just means find the voltage because everything's going to have the same voltage. And what that means is combine these three into one resistor and then multiply that by the current because V equals IR or V bar equals I bar Z. We want to find this Z because we already have the I, right? So we just have to put these three things in parallel. So these three in parallel, let's start with the capacitor and the inductor. So the ZL in parallel with ZC is going to be, ZL plus or ZL times ZC over ZL plus ZC. which here is J10 times negative J5 over J10 minus J5, right? Or plus minus J5. Remember, J is the square root of negative 1. So if there are two J's and they're multiplied by each other, they would get negative 1. So you'd get negative 1 times 10 times 5, or 10 times negative 5 then is like negative 50. And then on the bottom, we have J10 minus J5 is going to be just J5. And then you can simplify this a bit. This is 50 over J5. 1 over J is negative J, right? If J is the square root of negative 1, right? Then 1 over J would be, yeah, it's negative J. I could talk about it, but I don't want to. Um, so here, this ends up being negative J10, right? Because the 50 over 5 is 10, and 1 over J is that, and you get negative 10. So that's the first one. And then we'll call this Z1, right? So these two together make us Z1. And then we want 20 ohms in parallel with Z1. And that, just like how we did before, is going to be 20 times the thing we just found. So 20 times negative J10 over 20 minus J10, right? And this is going to be what, negative 200J over 20 minus J10. I'll go through the whole thing here. Basically, what you have to do is you then have to make the denominator real. So you do that by multiplying by the conjugate, which is 20 plus J10 over 20 plus J10. And that gets us like uh oh wait, that's kind of interesting what they did there. Eh. Oh wait, I'm looking at the huh. Okay, yeah, there's a couple ways to do this question. You could do it with like a source transformation, but I'm going to do it this way instead. So here it's 20 times 200 is gonna be like negative 400, 4000 J. And then this will be plus 2000. Yeah. And then over, it'll be 20 squared, or what, 20 squared minus 10 squared, I think. Let me make sure that's right. 20 minus 10J times 20 plus 10J in my calculator. Oh, oh, it's a real, it's them squared added together. Okay, so it's 20 squared plus 10 squared. So that gets us this, right? And then this you can just divide. So this is like 40 over 5 and 20 over 5. 40 over 5 is, so it'd be negative 8J plus 4. Is that the same thing we had last question? I swear I saw the number before. No, no, this was 8 plus 4J. This is 8J plus 4. Okay. Which I'll rewrite as 4 minus J8 because that looks slightly nicer. So we've simplified the circuit. It is now written as 0.2 amps, and then we have this equivalent Z equivalent, which has a value of 4 minus J8. And we want to find, okay, what is the voltage? Well, voltage equals IR or IZ. So the voltage is going to be 0.2 times 4 minus J8, which is 0.8 minus J 1.6. However, this cannot be your final answer because we have to turn it into phasor form. Uh, yeah, we have to turn this into phasor form. So the same way we did before. Basically, if it's asking you for a voltage or a current, you have to give it in phasor form. If it's asking you for an impedance, you can leave it in this form. But anyway, right at the end here, we got to do what? Did I do this right? Let me make sure I'm doing this right. 0.8 squared. Yeah, okay, cool. So this, square root of 0.8 squared plus 1.6 squared, that gets us 1.79, or like 1.78-ish. And then and then that theta equals the inverse tangent of negative 1.6 over zero point 0.8, which before you do this, it's good to think about the unit circle, right? And we got it because the tangent inverse function on your calculator will only give you stuff in this half. It like limits it from a positive to negative 90, I think, on the output. So here, however, we have minus 1.6 plus zero point 0.8. So here, so when we do the tangent inverse, it'll give us like this number because it's the same when you do the division. So you'll have to add 180 to your answer to get the actual answer here, I think. Right? Yeah. Oh, wait, no, it's minus 1.6J. So actually, ignore what I just said. It's not it's the real part that's positive. The imaginary part is negative. So it's actually down here. So it's within the range that your calculator will give you. So it's fine. Yeah. So here, if we do the tangent inverse of minus 1.6 over zero point 0.8, which is also just the tangent inverse of negative 2, we end up getting negative 63.43 degrees. So then our final answer for this voltage would be 1.78 e to the negative j 63.43 degrees. That'd be the answer. If how do you know when to add 180? I just said. So if if your real component is positive, right? Then in the complex plane, if your real so the reason you have to add 180 is because the tangent inverse function on your calculator, right? You give it some fraction imaginary over real, and then it turns this just like into some number and then gives you out a number. So it doesn't care about whether this is positive or negative or this is positive or negative. It just turns it into a number. And so for the sake of calculation, it only gives you angles like from positive 90 to negative 90. However, if you have a negative real component, right? So if you have a negative real component, that means that you're actually over here or over here. So if I plug in like if my number is like negative 2 plus j or something like that, right? Then I'd be over here. However, if I plug in to this formula, right, I put in one j is just like 1j, right? So if I put 1 over negative 2, that's the same as putting negative 1 over 2 in terms of here. So you have to think about, okay, if I have a negative real component, then it's going to be 180 degrees off from there. Um, to the question, do you not need to put it in the cosine omega t plus angle form? For this question, you don't. Notice that at the beginning of the question, it's already given to you in this form. Omega is not given, so you don't have to care about it. If omega isn't given, then you can just leave it in this form. However, if it was like this question where it was given to you as like these originally and you have an omega, then you do have to convert it back. However, if it's given to you converted, then it's fine. Can you do one node voltage problem with the reference node problem? I can do another. Let me see if I can find another node voltage problem. Yeah, I'll do one more node voltage problem here. Um, yeah, so in summary, yeah, if real is negative, you need to add 180. That's a good way to think about it. Yeah. Okay, quick thing with this question. You see here that the voltage is given as J6. So you can just like write it like that when you're doing the math. But it's good to think about this means that the equivalent, if you think about this in terms of like the phasors, right? You could actually like convert this by saying, okay, the magnitude, if this is 0 plus 6j, then the magnitude is 6, and the angle would be the inverse tangent of 6 over 0. Actually, that doesn't work. Oh no. So what this is where it's useful to think about the complex plane, right? Because if you have 6j, right, in the complex plane, that's just like straight up here. So if you think about it in terms of like an angle, right, this is going to be 6 times e to the j 90 degrees because 90 degrees is straight up. So you can use like either of these when you're doing your math. That's just a good thing to be able to like do off the top of your head. So this is just doing write the node voltage equations. So what are the essential nodes? So we label the bottom one as ground as always. So this is 0 volts. Here's one node. This is V1. And then here's another node. This is V2. This is also V2, right? Yeah. And then we just write the node voltage equations. So for V1, we got going down, we have V1 minus 0 over, okay, we have two things in series here. So we can just add them together, right? So this is just 4 minus J4, right? Or 4 plus minus J4. Cool. Going to the right, we have V1 minus, so going to the right, it's like this. We have V1, and then here we have a 12-volt difference between these points, but it's positive on this side. So here, if we have V2 here, then go down 12, we'd have V2 minus 12. So it'd be V1 minus V2 minus 12. And that over just that 3 ohm resistor here. And then going up out of there, we have V1, it's also minus V2 over 2 equals 0. Yeah. And then at V2, we simply have V2, or I'll start with the left path. So here, same as before, we have that V2 minus 12 minus V1 over 3. And then going down, we'll have V2 minus 0 over here. Again, we can just add these together. So it's 5 plus J7. And then, so we've done this, and then looking at what else is connected to V2, okay, we have this path and we have this path. So I'll do going up first. Going up, we have V2 minus V1 over 2. And then going down, we have V2 minus 8 over that, or no, sorry, V2 minus that J6 over 8 equals 0. And if it was just asking you, write the node voltage equations, this is your answer, and you're done. Yeah, I have 5 minutes left and my voice is running out, so I will give like a minute for if anyone has any questions to write in the chat. Otherwise, I will call it here. What question should we expect on the quiz? I'm hesitant to say that I know because I don't know. But it's gonna be something like the homework. It's gonna be something relating to, it'll just be like a basic circuit, but the components, you'll be expected to convert it to frequency domain, or it'll already be in frequency domain. It'll be something like these questions. I don't know exactly what. But like, yeah, make sure you know, I'd say the important things to know is make sure you still remember how solving resistors work. For calculators, should we use it in degree mode? Like, if you want, uh, yeah, if you want to get the number out of the tangent inverse, yes, you should. But like it still depends on, yeah, I guess the answer is yes. I'll upload my calculator video as well though. But yeah, I don't know if it's up to date, but I mean it doesn't really change. But anyway, yeah, make sure you know these. This is the important thing. This is like the only real thing you need to know. That and this. These are the only things you have to memorize. And then it's literally just resistor circuits, but with complex numbers. It's conceptually not that hard. The hard part is just not messing up your math somewhere along the way. Yeah. And this goes both ways. Yeah. Cool. in that case, I will end the recording here.